Okay, hello everyone. It's just now 2 o'clock. I'm going to wait a couple minutes to see if anyone else joins. All right, I'm going to start. Okay, next we'll take a look at chapter 14, which is ethers and epoxides. Okay, this is a propyl people ether. And this one is the ether bunny. Okay, I'm going to share my screen. Okay. All right, ethers, epoxides, and thioethers. All right, the general formula for an ether is ROR prime. R can equal R prime, but it doesn't have to. And R can be either alkyl or aryl. So ethers can be symmetrical or unsymmetrical. Okay, if we start with water, and if we replace one of the hydrogens with an R group, then we have an alcohol. If we replace both of the hydrogens with R groups, then we have an ether. Right, this one is diethyl ether. This is an unsymmetric one. We would name one group and then the other and then the word ether. So this is methylphenyl ether. And this one is tetrahydrofuran. Okay, because oxygen has 4 electron domains around it, the molecular geometry is bent. We have 2 bonds and 2 lone pairs. Oxygen is sp3 hybridized. The COC bond angle is about 110 degrees in dimethyl ether, and the CO bonds are polar. The molecule as a whole does have a dipole moment. Okay, compared to alkanes of comparable molecular weight, and then water and ethanol here are added for comparison. If we compare dimethyl ether with propane, okay, we can see that dimethyl ether has a little bit higher boiling point, not much. It is a gas at room temperature. Its boiling point is much lower than ethanol or water. Okay, and that's because these can hydrogen bond, but dimethyl ether cannot. Okay, one butanol, or butan-1-ol, has about the same molecular weight as tetrahydrofuran and diethyl ether. But you can see that for the diethyl ether, the boiling point is much lower. In fact, diethyl ether is almost the same as pentane. Although ethers cannot donate hydrogen bonds, they can accept hydrogen bonds because of the lone pair of electrons. So they have some solubility in water and alcohols. Okay, here are some of the physical properties. We've looked at boiling points of a few of these. Mostly ethers have a density less than water, okay, below 1. And when we do extractions, particularly with something like diethyl ether, the ether layer is going to be on top. Okay, here are some examples of ethers that are very commonly used as solvents. Okay, we have diethyl ether here, which you all have used in the lab. It boils at 35 degrees Celsius, which is about 95 degrees Fahrenheit. So if we have a really warm laboratory, the ether will boil. Okay, this one is 1,2-dimethoxyethane, abbreviated DME, and it has a common name called glyme. Okay, THF, or tetrahydrofuran, is a cyclic ether. Its IUPAC name is actually oxalane, but commercially it's much more commonly known as THF, or tetrahydrofuran. All right, this one is called 1,4-dioxane. We start counting at the oxygen here, so 1, 2, 3, 4. Okay, some of the properties of ethers include the fact that they are widely used as solvents because they can dissolve many nonpolar and polar substances, and they are unreactive toward strong bases. Ethers can solvate cations, but not anions. In contrast, alcohols will solvate both cations and anions. And so a substance such as lithium iodide is moderately soluble because the small lithium cation is strongly solvated, but the iodide is not well solvated. Ethers are essential solvents in such things as Grignard reagents and also for stabilizing electrophiles. Okay, in fact, when we prepare a Grignard reagent, we actually have to use either ethyl ether or tetrahydrofuran, and this is why. The ether coordinates with the magnesium and helps stabilize the complex. B2H6, which is the dimer of borane, is very reactive. It's also a gas, but we can stabilize it with THF. We can make this borane THF complex, and we can purchase borane THF in solutions of known molarity. So if you can measure out by volume however many equivalents of borane THF that you want. All right, these are crown ethers. In 3 dimensions, they're kind of shaped like a crown. There's a hole in the middle. 18 crown 6 solvates potassium ions tightly. Sodium ions are small enough where they would just rapidly move in and out. 15 crown 5 is just the right size for solvating sodium, and 12 crown 4 solvates lithium. Okay, 18 indicates it's an 18-membered ring, and then the 6 indicates the 6 oxygens here. Okay, looking at the electron paramagnetic map, you can see that the inside is electron dense, so it strongly attracts these cations, which are positively charged. The outside is hydrophobic. And so this allows polar ionic inorganic salts to dissolve in nonpolar organic solvents. One example is something called purple benzene, where we take potassium permanganate, KMnO4, complex it with this crown ether, and it will dissolve in benzene. Okay, even though KMnO4 without the crown ether would be completely insoluble. Okay, I've alluded a little bit to the common names. Okay, we name the 2 alkyl groups or aryl groups, attach the oxygen, add the word ether. We typically name the groups in alphabetical order. And for symmetric ethers, we use dialkyl or just alkyl. Okay, so this gets kind of confusing because diethyl ether is actually the same thing as ethyl ether. And when we talk about ether, we're usually referring to diethyl ether. All right, this one is tert-butyl methyl ether. We name one group and then the other. All right, in the IUPAC, the smaller group is named as an alkoxy group. Okay, so our parent compound here is propane, and OCH3 is a methoxy. Okay, so this is 2-methyl, 2-methoxy. Okay, I think it should actually be 2-methoxy, 2-methyl, since this comes first in the alphabet. Okay, the common name for this one is cyclohexyl methyl ether. In the IUPAC, it would be methoxy cyclohexane. Okay, there are a number of cyclic ethers. in which oxygen is part of the ring. The three-membered ring is called an epoxide or an oxirane. A four-membered ring is called an oxetane. Five-membered ring is an oxalane. This one is called furan, with the two double bonds. This is pyran, oxanes, and then this is 1,4-dioxane. Okay, looking at epoxides and their nomenclature, using the common name, we first name the alkene that it was prepared from. Okay, so we are forming an epoxide of cyclohexene. So we would call this cyclohexene oxide. Okay, in the IUPAC, there are a couple of different ways of naming epoxides. Okay, for this one, this is trans 1,2-epoxy 4-methylcyclohexane. Okay, so we actually need two numbers to locate an epoxy group. So 1,2-epoxy 4-methylcyclohexane. Okay, for this one, the longest chain is 1, 2, 3, 4, 5, 6. And there's an epoxy group between 2 and 3. There's a methoxy group on 4. So this is cis 2,3-epoxy 4-methoxy hexane. Okay, this is cis because you can see both hydrogens are up. Okay, if these were switched, then it would be trans. Okay, you could also refer to the three-membered ring as the parent compound, oxirane. And when you do that, the oxygen is position number 1 and the carbons are 2 and 3. Okay. Right, so this could be named as oxirane. Could also be named as 1,2-epoxy ethane. Right, this one, okay, if we consider this to be the parent, okay, this is oxirane, and so it would be 2,2-diethyl 3-isopropyl oxirane. Okay, we want to give these the lowest set of numbers. Oxygen is position number 1. All right, we could also go this way. Okay, and we could call it 3,4-epoxy 4-ethyl 2-methylhexane. Okay, here's another one. Okay, so this is trans 2-methoxy 3-methyloxirane, or 1,2-epoxy. Okay, this is position number 1 if we're doing it that way, 1-methoxy propane. Okay, both names are correct. Both are IUPAC. Okay, I posted a video on Top Hat for this week's lab about infrared spectroscopy. Infrared spectroscopy looks at the bond stretching frequencies, and this gives them information about the functional groups that are present. So in the infrared, the CO stretch occurs at about 1,000 to 1,200 wave numbers. Okay, many compounds besides ethers will have this CO stretch. We can look for other groups like if we don't see a CO double bond or an OH stretch, then it's likely it's an ether. Okay, I posted another video about mass spectrometry. So we vaporize a sample, we shoot it with high energy electrons. This causes first an electron to be knocked loose from the sample, and then it causes fragmentation. The detector will detect cations, and the most stable cations tend to be the most abundant ions. Okay, so for ethers, there are two principal modes of cleavage. One is what is called alpha cleavage, where we start from the oxygen. Between the first and second carbons, it breaks apart. Okay, so we get a R free radical, which is not observed. The detector is only detecting cations. And we have this oxonium ion, which is resonance stabilized. So we would expect this to be an abundant ion. Okay, the other way in which ethers are cleaved are right next to the oxygen. Okay, this also gives us an oxonium ion. Okay, when it picks up an H, we can also get an alkyl cation. The corresponding alkoxy free radical is not observed. Okay, again, the detector is only observing cations. Okay, so the molecule is fragmented. It starts out under high vacuum. There's a high purity gas, such as high purity helium, which sweeps the sample downstream and use some kind of a mass selection device like a magnetic sector. And so different masses will reach the detector at different times. Right, so here is diethyl ether. It has a molecular weight of 74. And so this peak at 74, that represents this with one electron knocked loose, so that you have a cation. All right, then this goes on to lose a fragment of 15 mass units. Okay, that would be a methyl group. Okay, so that's alpha cleavage. And then we can also see a loss of 45, which gives loss of 29, which is an ethyl group, which gives this peak at 45. And then another alpha cleavage, which is what I just mentioned, where we lose a methyl group. Okay, that gives this peak at 59. And then the mass at 31 is a result of first alpha cleavage and then splitting out an ethylene. Okay, ethylene is a neutral molecule, so it's not detected. So we just detect this, this resonance stabilized ion. Okay, I haven't talked about NMR. That will be next week's lab. But NMR gives the electron environment around certain isotopes. The vast majority of NMR involves hydrogen-1. You can also do NMR with carbon-13, and I will talk about that in more detail. Okay, but the value along the x-axis for this proton on the alpha carbon shows up between about 3.5 and 4 delta units. For the carbon, and the scale is about from 0 to 10. Okay, so this value tells you something about the chemical environment. Okay, there's an oxygen nearby. For the carbon-13, okay, we see a signal at somewhere between 65 and 90. All right, next we'll look at Williamson ether synthesis, and we've actually seen this in a couple of previous chapters. Okay, so if we have an alkoxy anion, okay, which we can generate by using a strong base and an alcohol, or we can use an active metal like sodium or potassium. Okay, this can do an SN2 reaction on a substrate, and the substrate has to be an unhindered primary halide or tosylate. Okay, it could also be a methyl. The alkoxide, as mentioned, is commonly made by adding sodium, potassium, or sodium hydride to the alcohol. Okay, so here are some examples of the Williamson synthesis. All right, so we start off with cyclohexanol. We use sodium to reduce hydrogen, and that gives us the alkoxy. And then we can do an SN2 with ethyl tosylate. So this will attack carbon number 1 here, kick out the tosylate, and then we get ethoxy cyclohexane. Okay, this is another way of generating alkoxy ions, and that's to use sodium hydride. Okay, so hydrogen or hydride pulls off this hydrogen, we get hydrogen gas. And then this goes on to do an SN2 with iodomethane. It attacks carbon, kicks out the iodine. And then the resulting compound is 2-methoxy 3,3-dimethyl pentane. Okay, we saw a couple of chapters ago that phenols are many times more acidic than alcohols. And so to form the phenoxide, the O-, okay, we don't have to use sodium hydride or sodium or potassium metal. We could use sodium hydroxide or even sodium carbonate. Okay, that forms the phenoxide, and then we can do an SN2 to form the desired ether. Okay, so this one is 2-butoxy nitrobenzene. Okay, this is an important point. Phenyl halides or tosylates cannot be used for this synthesis method. Okay. Okay, so here's what they're talking about. This would not work. Okay, this would not work by either SN2 or SN1. It cannot undergo SN2 because this can't get into the back side. Okay, it would actually have to get inside this electron-rich ring. which it can't do. And this carbon cannot undergo inversion. Okay, remember in an SN2 there's inversion. Okay, so that's not going to work. What about SN1? Well, the resulting phenylcation is pretty unstable, so that's not going to work either. Okay, so if we're making an alkyl phenyl ether, okay, the alkoxide has to be an alkyl. Okay, we also can't use tertiary halides or tosylates. Okay, so let's say we want to make tert-butyl propyl ether. Okay, this is not going to work because what we'll get instead is E2 elimination. Sodium propoxide removes a beta hydrogen, we form the double bond, we kick out the bromine. All right, but if we use a different set of starting materials, okay, instead of sodium propoxide, let's use sodium tert-butoxide and 1-bromopropane, which is a primary halide. Okay, then it works. Okay, back in our alcohols chapter, we talked about oxymercuration, demercuration. If we use an alcohol instead of water as our solvent, we can make an ether. Okay, this follows Markovnikov's rule if we have an unsymmetric alkene, such as hex-1-ene. Okay, rich get richer, so hydrogen goes here. And since we're doing this in methanol, we'll get a methoxy group at position number 2. Okay, and this is the same mechanism as oxymercuration, demercuration. Okay, and then we use sodium borohydride in the last step to take off the mercury. Okay, both ethanol and diethyl ether are prepared industrially in huge amounts. Okay, we can do a bimolecular condensation of 2 molecules of ethanol at 140 degrees Celsius. If the temperature is too high, then we get ethylene. We get the corresponding alkene. That takes place at about 180 degrees Celsius. Okay, this is really not a good lab synthesis. It is an industrial method. Okay, you can make di-N-propyl ether by this method. If you start with a secondary alcohol, however, you're going to get dehydration, so no ether will form. Okay, so your alcohol has to be primary. Okay, it also has to be symmetric. All right, so if we tried to make ethyl propyl ether by this method, we would get every combination. We would get diethyl ether, we get ethyl propyl ether, we get dipropyl ether. Okay, so this only works with small symmetric ethers. And it only works starting from primary alcohols. Right, next we're going to look at cleavage of ethers by HR, HBr, and HI. Ethers are actually unreactive, and this makes them good solvents for a lot of different reactions. They can be cleaved by heating with concentrated HBr and HI. HI is more reactive than HBr. Okay, so here's the mechanism. Okay, so the ether oxygen picks up an H, it becomes protonated. Br minus then comes in and attacks from the backside and kicks out this alcohol. If we're using excess HBr, the alcohol, okay, that's formed here, can react further to produce another RBr. Okay, and this is an important point. This reaction does not occur with aromatic alcohols, phenols. Okay, and here is an illustration of that. Okay, while a dialkyl ether can form two equivalents of the alkyl bromide, a phenyl ether can only cleave on one side. Okay, so the mechanism starts out the same. Oxygen gets protonated. The bromide has to attack the CH2. Okay, it cannot attack here. Okay, so you only get phenol and ethyl bromide. The phenol does not react any further. Right. Autoxidation of ethers is a serious unwanted problem. Okay, in the presence of atmospheric oxygen, which is itself a diradical, ethers can slowly oxidize to form hydroperoxides and dialkyl peroxides. Okay, both of these can be highly explosive. Okay, so some of the ways of avoiding this. Okay, first of all, if you're doing a reaction that involves an ether and you're doing a distillation, do not distill to dryness or near dryness. Okay, because as the peroxides become more concentrated, they become much more prone to explode. Okay, when we order ether for the department, we avoid adding, we avoid ordering 5-gallon or 1-gallon containers. Instead, what we do is we'll order several of these 1-liter cans. Okay, because once the bottle is opened, then it becomes exposed to oxygen in the air, and over a period of time, these peroxides can form. Okay, with these smaller bottles, we use up the ether more quickly. Okay, so if a bottle has been opened and stored for a long period of time, then it's very prone to forming these hydroperoxides and alkyl peroxides. Okay, one of the worst things you can store ether in is a clear glass bottle with a ground glass stopper. Okay, peroxides can be decomposed on exposure to light, and then they can also be set off just by mechanical shock. So if there's any peroxides in the neck of the bottle or the flask, and you turn that stopper, you can detonate peroxides. Okay, so we get our ether in either tin or aluminum cans. Okay, first of all, it's opaque, so that avoids exposure to light. Also, tin or aluminum serves as a reducing agent to help reduce the peroxides. And so a warning sign if you're using ether is to look for rusty cans. Okay, if the can is rusty, then that is an indication that you might have peroxide. All right, so here's the mechanism of autoxidation. Okay, from oxygen in the air, this occurs slowly. It may take several weeks or months to form these peroxides, or here's a hydroperoxide, OOH. Right, thioethers are the sulfur analogs of ethers, and we can name these by replacing the word sulfide for ether. Okay, so this is dimethyl sulfide, this is methylphenyl sulfide, and as a substituent, we could call this ethyl thio, so 4-ethyl thio, 2-methyl pentuene. Okay, in this case, the alkene takes priority. Okay, these thioethers can be formed from thiolates. We can form the conjugate base of a thiol and then do an SN2. Okay, so this one is ethyl propyl sulfide. This is very similar to the Williamson ether synthesis that we just looked at a few minutes ago. Okay, in terms of reactions, sulfides react very differently than ethers do. Okay, they're easily oxidized to sulfoxides and sulfones, both of which are actually stable functional groups. Okay, so this is a sulfoxide, and then on further oxidation, we can form this sulfone. Sulfides can also act as neutral nucleophiles. They can undergo SN2 reactions to form what are called sulfonium salts. Okay, the sulfur was neutral, and when it gained this third bond, it's now positive. Thioethers can act as reducing agents, okay, such as in ozonolysis. Okay, so we split this double bond with ozone. Okay, one oxygen goes here, one goes here, and the third goes with the sulfur to form dimethyl sulfoxide. Okay, so these are mild reducing agents. Silyl ethers are those in which we have a silicon on one side of the oxygen. Silyl ethers are resistant to many acids, bases, and oxidizing agents. They are more easily formed and more easily hydrolyzed. One very common use of silyl ethers is as protecting groups for alcohols. Okay, here's one example. Okay, so let's say we want to do a Grignard. Carbonyl is polarized, carbonate is plus. Grignard attacks the carbon nucleus. Okay, but this OH presents a problem because that's acidic, and instead what happens is a Grignard reacts with it. Okay, but if we protect that OH as a silyl ether, okay, then we could carry out that reaction and then remove the silyl ether when we're done. Okay, so silyl ethers are typically made from silyl chlorides. Triethylamine is a base. What it does is it neutralizes the HCl that's formed. And when we want to remove the silyl group, we can use something like tetrabutyl ammonium fluoride. turns out that silicon has a very strong attraction for fluoride, much stronger than that for oxygen. So that takes a silyl group off. Sulfonium salts can also be used as alkylating agents. Okay, so we use a nucleophile, which then attacks one of the alkyl groups and kicks out the sulfide. Okay, here is a review of synthesis of epoxides. Okay, we use a peroxy acid. Okay, maybe something like MCPBA. MMPP is another epoxidation reagent. Okay, this is more soluble in polar solvents. The most electron-rich double bonds react faster. Okay, so this on this side, the one with the two methyl groups, this is the more electron-rich group. So that gets epoxidized first. Okay, here we have MMPP. This is carried out in water and acetonitrile. Okay, more polar solvent. Okay, this is also a review halohydrin formation where we use water and chlorine or bromine. We can also form epoxides from halohydrins. Okay, because of the presence of this nearby halogen, that renders this hydrogen more acidic. So just using hydroxide or a similar base, we remove that, we form the anion, and then this does an internal SN2. Oxygen attacks the carbon, kicks out the halogen, we got the epoxide. Okay, and here is an example. Okay, so we form the halohydrin, and this works because the OH and the chlorine are trans to each other. Okay, so OH removes this proton, we form the anion, which then attacks this carbon, kicks out the chlorine. Okay, next we'll look at ring opening of epoxides. Okay, in acid solution, oxygen gets protonated first, water attacks, and since this is symmetric, it doesn't matter which side. So water attacks and it breaks open this ring. Okay, then another water removes a hydrogen and we get a trans diol. Okay, if we use alcohol as our solvent instead of water, okay, it's the same mechanism except we get an alkoxy alcohol. We get an alkoxy group and an alcohol group that are trans to each other. The alcohol takes priority in naming, so this is trans 2-methoxy cyclopentanol. Okay, we can also open up epoxides in base. Okay, the order of the steps is reversed. So instead of protonating, the nucleophile attacks first, and it opens up the ring, and then O- picks up a proton from water. Okay, for most ethers, this base catalyzed ring opening doesn't happen. Okay, because the activation energy is too high. The base is usually stronger than hydroxide, so that doesn't make it favorable either. With epoxides, you have ring strain, and so that favors attack and ring opening, and the reaction is exothermic. Okay, we can open up rings with hydrogen halides. Okay, this ultimately gives a 1,2 dihalide. All right, in terms of regioselectivity, if we have an unsymmetric epoxide such as this, in acid solution, the nucleophile attacks the more substituted side. Okay, so the ethoxy group will end up here on the left. In basic solution, the nucleophile attacks the less substituted side. Okay, I'll mention this just very briefly. We have about a minute or so left. Epoxide formation is important in the biosynthesis of steroids, such as cholesterol. Grignards and organolithiums can also attack epoxides. Since there are very strong nucleophiles and strong bases, they'll attack the less substituted side. And then finally, epoxy compounds are important in the formation of epoxy resins. And epoxy glues, these polymerize in place, so they match the shape of the joint perfectly. Okay, and we can make, okay, this is a continuation. This is a polymer formation. And that is it for today. So I'll go ahead and stop there.